Between the galaxies you have seen in every photograph, between every cluster and supercluster astronomers have ever mapped, there is something far larger than all of them combined. It is not a wall of galaxies. It is not a supercluster stretching across billions of light years. It is almost nothing. A region of space so staggeringly vast and so profoundly empty that it dwarfs every structure the universe has ever built. Scientists call it a cosmic void. The largest one ever discovered spans nearly 2 billion light-years across. A region of space where roughly 1 in every 5 galaxies that should exist is simply missing. What makes it terrifying is not what lurks inside this region. It is what the void reveals about the universe itself. Most of it is missing. If you enjoy journeys that permanently change how you see reality, do me a small favor and hit that like button and subscribe. It genuinely helps this channel continue making content like this. And I truly appreciate every single one of you. Now, let's dive in. For most of human history, we assumed the universe was more or less evenly filled with stars and galaxies. It seemed reasonable. Point a telescope in any direction and you would find something shining back at you. The night sky looked crowded, peppered with matter scattered in every direction as far as our instruments could see. Astronomers spent centuries cataloging this apparent abundance, counting nebulae, mapping star fields, and classifying galaxies by their shapes. They were gradually building a picture of a cosmos that seemed, at its largest scales, satisfyingly uniform. Galaxies were everywhere, and everywhere looked roughly the same if you zoomed out far enough. This assumption became so deeply embedded in modern cosmology that it earned a formal name: the cosmological principle. The universe, viewed at sufficiently large scales, should be homogeneous, meaning it looks roughly the same in every location, and isotropic, meaning it appears the same in every direction. It was elegant, mathematically convenient, and for a long time it seemed to match every observation available. Then, in the late 1970s, that picture began to unravel. The shift started with a deceptively simple ambition. Astronomers wanted to build a three-dimensional map of the universe. Every sky survey up to that point had essentially been flat. They could tell you where a galaxy appeared in the sky, its coordinates projected onto the dome above Earth. But they could not tell you how far away it actually was. Two galaxies sitting side by side in a photograph might be separated by billions of light-years in real space. One relatively nearby and the other staggeringly distant. Without that third dimension, without depth, astronomers were trying to understand a three-dimensional structure using a two-dimensional picture. It was like trying to map a mountain range using only its shadow on the valley floor. You could see that something large existed, but you could not tell whether two peaks were actually next to each other or separated by vast distances along a direction you simply could not measure. The tool that finally solved this problem was redshift. As the universe expands, it stretches the fabric of space, and light traveling through that expanding fabric is stretched along with it. The wavelengths grow longer, shifting toward the red end of the spectrum. The farther a galaxy is from Earth, the more the intervening space has expanded since that light was emitted, and the more its light has been reddened. By measuring the precise degree of redshift in a galaxy's spectrum, astronomers can estimate its distance. This technique was not new. Edwin Hubble had used it decades earlier to demonstrate that the universe itself is expanding. But applying it systematically to thousands, and eventually tens of thousands of galaxies in coordinated surveys, was a project of an entirely different scale. It required new spectrographs capable of splitting the faint light of distant galaxies into their component wavelengths. It demanded enormous amounts of telescope time, sometimes spanning years of observation, and it required painstaking data analysis, transforming raw measurements into precise three-dimensional positions. galaxy by galaxy. In 1978, two teams working independently began publishing the first results, and both discovered something unexpected. Stephen Gregory and Laird Thompson mapped a wedge of the sky in the direction of the Coma galaxy cluster. Plotting the three-dimensional positions of galaxies across hundreds of millions of light-years. The distribution was not smooth. It was not even close to smooth. Galaxies clumped together along elongated chains and concentrated at certain distances, leaving enormous gaps between them. Regions tens of millions of light-years across appeared to contain almost nothing. Where theoretical models had predicted a relatively even scattering of galaxies, like grains of rice spread across a table, the observations revealed something strikingly different. Galaxies were arranged along narrow structures, separated by vast, yawning voids. The uniformity that cosmologists had relied upon, the assumption that had simplified their equations and anchored their models, simply was not there. The universe had structure at scales nobody had anticipated. At almost the same time, astronomers Jan Einasto and Michael Jovier at the Tartu Observatory in Estonia arrived at strikingly similar conclusions from a different portion of the sky. In 1978, they announced that the universe appeared to have a cellular structure, with galaxies arranged along the walls of enormous cells that enclosed vast, largely empty interiors. The claim was radical. The prevailing model assumed that matter distributed itself randomly and smoothly at large scales. A foundational assumption embedded in the governing equations of cosmological physics. The idea that the universe might be organized into walls and voids sounded almost architectural, as if the cosmos had been assembled according to some hidden blueprint. And the most provocative part of their finding was not the walls themselves. It was the enormous emptiness those walls surrounded. The cells they described were not small gaps between neighboring clusters. They were vast hollow regions, spanning hundreds of millions of light-years. And there seemed to be many of them. The confirmation arrived quickly. Throughout the early 1980s, larger redshift surveys began mapping deeper into space. And every one of them revealed the same unsettling pattern. Galaxies were not uniformly scattered throughout the cosmos. They formed intricate networks of filaments and walls that enclosed enormous, bubble-like empty regions. The deeper astronomers probed, the more organized the universe appeared, and the more prominent the emptiness became. Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics produced one of the most famous visualizations in astronomical history with their CFA redshift survey. A slice of the cosmos that revealed galaxies strung along thin arcs and walls surrounding vast empty bubbles. The universe looked less like a smooth ocean and more like a sponge. A vast three-dimensional lattice of matter surrounding pockets of almost nothing. The more astronomers mapped, the more holes they found, and the holes kept getting larger. The most dramatic early demonstration came in 1981. Robert Kirshner, Augustus Umlayer, Paul Schechter, and Stephen Schechtman had been conducting a redshift survey of galaxies in the constellation Boötes when they stumbled upon something that should not have existed. In a volume of space approximately 330 million light-years in diameter, they found fewer than 60 galaxies. 60. To appreciate how extreme that deficit is, you need to understand what that same volume of space should normally contain. A typical region of that size in the observable universe, based on the average density of galaxies measured across billions of light-years of surveyed space, should contain several thousand galaxies. The Boötes Void was not just a little sparse. It was a desert, an enormous sphere of cosmic real estate from which galaxies were almost entirely absent. If our own local group of galaxies existed at the center of the Boötes Void, the nearest major galaxy cluster would lie so far away that it would barely register even in our most powerful telescopes. The night sky, stripped of almost all external galaxies. would look profoundly lonely. The discovery made headlines and created immediate tension within the cosmology community. A void that large was difficult to reconcile with the standard model of how cosmic structure forms. In the prevailing picture, the universe began in an almost perfectly uniform state after the Big Bang, with minuscule density fluctuations seeded by quantum processes during the first fraction of a second. These fluctuations were extraordinarily tiny. Variations of roughly 1 part in 100,000 from the average density. Yet over billions of years, gravity amplified those fluctuations. Regions with slightly more matter than average attracted even more matter from their surroundings, growing progressively denser. Regions with slightly less matter lost what little they had to their denser neighbors, becoming emptier. This process, known as gravitational instability, is well understood mathematically. It has been modeled extensively and produces results that match many observations of cosmic structure. But producing a void as enormous as the one in Boötes requires initial conditions that are statistically uncommon. The models predicted plenty of small voids. Modest, underdense pockets, tens of millions of light-years across, scattered throughout the cosmic web. A void stretching over 300 million light-years pushed the boundaries of what random fluctuations could comfortably produce within the standard cosmological framework. Some cosmologists argued that the Boötes Void was simply a rare event, a statistical outlier sitting at the extreme tail of the probability distribution. Improbably, but not impossible. Others suspected it pointed to something deeper. A clue that structure formation in the universe might be more vigorous and more extreme than existing models had predicted. And yet, regardless of the debate, the void was real. It had been confirmed and measured by multiple independent surveys. It could not be dismissed as a data artifact or a calibration error. The Boötes Void forced cosmologists to take the structure of emptiness seriously, not as a curiosity lurking in the background of galaxy maps, but as a fundamental feature of the universe that demanded explanation. But understanding what a cosmic void actually is requires clearing away a common misconception. A void is not a hole punched into space. It is not a region where matter was removed, destroyed, or never existed. It is not the complete absence of everything. A cosmic void is simply a region where the density of matter, meaning galaxies, gas, and the invisible scaffolding of dark matter, falls far below the cosmic average. The universe has an average density, a value calculated from the total amount of matter spread across the entire observable volume of space. Dense regions such as galaxy clusters exceed this average by large factors. Sometimes, by hundreds of times, voids fall far below it, typically containing only 10 to 20% of the matter found in an average region of comparable size. That means voids are not truly empty. Galaxies still exist within them, scattered thinly through the darkness like isolated farmhouses across an enormous plain. Stars still burn. Gas still drifts in tenuous wisps, often too diffuse to collapse into anything new. Dark matter still permeates the volume, forming a faint, ghost-like web of invisible mass that connects these regions to the denser structures outside. But the matter is so sparse, spread across such colossal distances, that the gravitational forces which build structure elsewhere simply cannot operate effectively inside a void. This distinction between empty and underdense is crucial for understanding what voids actually do to the universe around them. An empty region, a true vacuum containing absolutely nothing, would be inert. It would simply be space, with nothing happening and no forces acting on anything. An underdense region, however, is something far more interesting and far more consequential. It is a place where the balance of cosmic forces tips in a fundamentally different direction. In the dense filaments and clusters where most galaxies reside, gravity is strong enough to pull matter together, resist the expansion of space, and build ever larger structures over cosmic time. Clusters grow by swallowing their neighbors. Galaxies merge in violent collisions that trigger bursts of star formation. Matter accumulates in the nodes of the cosmic web, like water collecting in the lowest points of a drainage basin. Inside a void, gravity loses that contest decisively. There is simply not enough mass to generate significant gravitational attraction across such enormous volumes. The dominant influence becomes dark energy, the mysterious pressure that drives the accelerating expansion of the universe. In dense regions, gravity can fight dark energy to a standstill, sometimes even winning and holding structures together against the outward push. Inside voids, dark energy wins outright. And when dark energy dominates, space expands faster. The void grows. This creates a feedback loop that shapes the evolution of the entire cosmos. As a void expands, it becomes even more underdense because the same small amount of matter now occupies a larger volume. Lower density means even less gravity. Less gravity means even less resistance to expansion. The void grows faster, becomes emptier, and accelerates its own growth in a self-reinforcing cycle. Meanwhile, the matter that once occupied the expanding void is gradually pushed outward, swept toward the boundaries where the void meets the surrounding filaments and walls. Dense regions become denser as this displaced material piles up along the edges. Empty regions become emptier as matter drains away. Over billions of years, this process carved the universe into the architecture we observe today. A vast cosmic web of matter surrounding expanding bubbles of near emptiness that grow steadily larger and more extreme over time. After the discovery of the Boötes Void, new findings followed rapidly. Observational technology improved dramatically with each passing decade. The 2-degree field galaxy redshift survey in the late 1990s mapped more than 230,000 galaxies in the southern sky, producing the most detailed 3-dimensional atlas of the nearby universe that had ever been created. Then came the Sloan Digital Sky Survey, which began observations in the year 2000, and eventually charted the positions and distances of millions of galaxies across billions of light-years of cosmic depth. Each successive survey peeled back another layer of structure, and every time the same unmistakable pattern emerged. Filaments threaded through space like the strands of an immense web. Walls of galaxies stretched for hundreds of millions of light-years in thin sheets. Dense clusters glowed at the intersections where multiple filaments converged. And between all of these luminous structures, filling the vast volumes between them, lay the voids. The Sloan survey produced some of the most stunning 3-dimensional maps of the universe ever assembled. When you look at one of these maps, the first thing that stands out is not the galaxies. It is the gaps. Bright points representing individual galaxies cluster along sinuous threads, forming a web-like lattice stretching in every direction across billions of light-years. But between those threads lie enormous dark bubbles where almost no galaxies exist. Some of these bubbles span hundreds of millions of light-years in diameter. They are not small irregularities in an otherwise smooth distribution. They are the dominant visual feature of the map. The impression is immediate and unmistakable. The universe has the texture of foam. Matter clings to thin surfaces and narrow channels while the vast interior volumes remain hollow. Scientists formalized this architecture under the name cosmic web. It is the largest known structure in nature, extending across the entire observable universe and organizing all visible matter into 4 distinct components. The first component is nodes. These are the densest regions, the intersections where multiple filaments converge. Galaxy clusters form at these crossroads, packing hundreds or even thousands of galaxies into relatively compact volumes spanning only a few million light-years. Nodes are the busiest neighborhoods in the cosmos. full of colliding galaxies. Superheated gas glowing at temperatures of hundreds of millions of degrees. And supermassive black holes devouring matter at their centers. The second component is filaments. These are the threads of the web. Elongated chains of galaxy groups, stretching for hundreds of millions of light-years between nodes. Filaments channel matter from lower density regions toward the dense clusters at their endpoints, acting as cosmic supply lines that feed galaxy formation in the most crowded regions of the web. The third component is walls, sometimes called sheets. These are broad, flat structures where galaxies spread out across immense surfaces connecting multiple filaments together. These are concentrations of galaxies that form where filaments meet along two-dimensional surfaces. Walls are thinner and more diffuse than filaments, but they extend across truly enormous distances. Some of the largest coherent structures ever observed belong to this category. The Sloan Great Wall, identified in 2003, stretches approximately 1.4 billion light-years in length. And then there is the fourth component, the one that occupies more space than the other three combined. The voids. Voids are not merely gaps in the cosmic web. They are its defining feature. Consider what occupies the most volume in a sponge. It is not the solid material forming the walls and channels. It is the open space filling the pores. The same principle holds at cosmic scales. The filaments, walls, and nodes of the cosmic web contain nearly all the visible matter in the universe. But they occupy only a minority of the total volume. The voids fill the rest. And the rest turns out to be almost everything. Quantifying this imbalance took decades of survey work and sophisticated statistical analysis. But modern measurements have converged on a figure that should permanently alter how you picture the cosmos. Voids occupy approximately 80 to 90% of the total volume of the observable universe. The filaments, walls, clusters, and superclusters that contain the overwhelming majority of galaxies, indigenous stars, gas, and dust are all packed into the remaining 10 to 20%. The universe is not a sea of galaxies with occasional gaps between them. It is a vast expanse of underdense space with thin threads of matter woven sparsely through it. This realization changes how you should imagine the cosmos at its largest scale. Every photograph of deep space, every Hubble ultra-deep field image packed with thousands of galaxies stretching back toward the edge of observable time. Every sweeping visualization showing clusters and superclusters reaching the limits of detection. All of those images capture only the thin minority of the universe where matter happened to concentrate. They show you the threads and nodes of the cosmic web, the crowded and busy places where galaxies formed and evolved. But the overwhelming majority of cosmic volume lies between those images. In the regions between the filaments, inside the enormous dark interiors of these bubbles, those regions are almost never photographed because there is practically nothing there to photograph. If you could shade a cosmic map so that void regions appeared in one color and matter structures in another, the map would be dominated by voids. The filaments would resemble thin scratches across an otherwise featureless canvas. Mapping voids with precision requires enormous datasets and careful statistical analysis. Scientists identify voids by comparing the observed distribution of galaxies to the expected average density. They divide surveyed volumes into cells, count the galaxies in each cell, and search for contiguous regions where the count falls significantly below the cosmic mean. Various algorithms have been developed to automate this process, each defining void boundaries according to slightly different mathematical criteria. But they all converge on the same broad picture. One particularly valuable method is called void stacking. Individual voids vary in shape, size, and depth, which makes it difficult to study any single void's internal structure in detail. But by averaging the profiles of hundreds or even thousands of voids together, aligning them by their centers, Scientists can build a composite portrait of a typical void. This average profile reveals a characteristic structure. Voids are deepest at their centers, where the density reaches its minimum. Moving outward, the density gradually rises until it reaches the boundary known as the compensation wall, a ridge of slightly above average density where matter pushed outward by the void's expansion has accumulated against the surrounding cosmic web. The sizes of cosmic voids span a wide range. Small voids measure roughly 30 to 50 million light-years across. These are the most common type, scattered throughout the cosmic web like tiny air pockets in carbonated water, filling the spaces between neighboring galaxy groups. Medium-sized voids stretch 100 to 300 million light-years in diameter. These are the standard building blocks of the cosmic foam, the characteristic bubbles that give the large-scale universe its distinctive texture. Then there are the supervoids, underdense regions exceeding 500 million light-years across. Supervoids are rarer and more difficult for standard cosmological models to produce. Generating one requires initial density fluctuations that were unusually smooth across enormous volumes, a condition the lambda cold dark matter model predicts should occur only infrequently. Each time observers discover a supervoid larger or deeper than simulations can easily account for, it places additional pressure on the theoretical framework. Computer simulations have become indispensable tools for understanding void formation. Scientists build virtual universes inside supercomputers, seeding them with the same initial conditions inferred from precise observations of the cosmic microwave background, and then running the gravitational clock forward for billions of simulated years. These simulations reliably produce cosmic webs that match reality remarkably well, complete with filaments, clusters, and voids arranged in patterns that closely mirror actual survey data. By tracking how simulated voids form, grow, and merge with neighboring voids over cosmic time, researchers can test and refine their understanding of the physics governing real cosmic structure. One key insight from these simulations is that voids are not static features frozen into the fabric of the universe. They evolve continuously. In the early cosmos, when matter was distributed more evenly and density contrasts were still extremely small, voids were shallow and modest in extent. As gravitational instability amplified primordial density fluctuations over billions of years, overdense regions collapsed into filaments and clusters, while underdense regions expanded outward into voids. This process mirrored the growth of dense structures, but in reverse. While clusters grew by accumulating matter, voids grew by losing it. The expansion of voids accelerated further as the universe aged and dark energy became the dominant component of cosmic energy over the last several billion years. In the current epoch, dark energy contributes roughly 68% of the total energy content of the universe, overwhelming the gravitational pull of matter across all but the densest regions. Today, voids are larger and emptier than at any previous epoch in cosmic history, and they continue to grow with every passing billion years. The cosmic web is not a fixed or permanent architecture. It is a dynamic and evolving structure that becomes more extreme over time. Its voids slowly widen, its filaments gradually thin, and the contrast between full and empty grows sharper as dark energy tightens its grip on the cosmos. But simulations have also revealed something troubling. While the standard cosmological model successfully reproduces the typical population of voids, it struggles with the largest and deepest ones. The biggest supervoids found in real sky surveys appear at sizes and depths that simulations produce only rarely. Either the simulations are missing an important piece of physics, the observations contain systematic biases that overestimate void properties, or the initial conditions of the universe allowed for more extreme structures than the standard model comfortably accommodates. This tension between theory and observation became one of the defining puzzles in the study of large-scale cosmic structure. That puzzle intensified beyond anything astronomers had anticipated when they began to uncover just how large the largest voids could be. The Boötes Void, roughly 330 million light-years across, was once considered extraordinary. A statistical anomaly pushing the limits of standard structure formation theory. Subsequent surveys revealed other large voids scattered throughout the cosmos, some exceeding 500 million light-years in diameter. Each discovery raised the same persistent question: was this the largest void we would ever find? Or was something far bigger waiting in the data? Too vast and too diffuse for earlier surveys to resolve, the answer, when it finally emerged, was not merely larger. It was so enormous that it redefined what astronomers believed a single cosmic structure could be. A void so vast that the Boötes Void could fit inside it thousands of times without making a measurable difference to its emptiness. A void so immense that entire superclusters, each containing hundreds of thousands of galaxies, lie within its boundaries. And yet the region still registers as profoundly underdense compared to the cosmic average. The scale was not an incremental step beyond previous discoveries. It was a leap into a category many theorists had once assumed could not exist. And the most unsettling part of that discovery was not its scale. It was not merely the number of missing galaxies or the staggering volume of underdense space. It was something far more personal. It was where the void turned out to be located, and what that location might mean for every measurement humanity has ever made about the cosmos. What makes the largest void so deeply unsettling is not what exists inside it. It is how much of the universe it occupies, and how it forces us to confront the possibility that the cosmos may be shaped less by the matter we see and more by the vast regions where that matter is missing. After the Boötes Void entered the scientific literature, astronomers began actively searching for others. They did not have to look far. Every new redshift survey that mapped a larger volume of the cosmos revealed more voids. Some comparable in size to Boötes, others smaller, and a few considerably larger. The cosmic web was turning out to be even more hollow than early observations had suggested. But the truly enormous voids, the ones that would eventually challenge theoretical cosmology, did not first reveal themselves through galaxy surveys. They revealed themselves through ancient light. The cosmic microwave background is the oldest light in the universe. It was released approximately 380,000 years after the Big Bang. At the moment when the primordial plasma cooled enough for protons and electrons to combine into neutral hydrogen atoms for the first time, before that moment, the universe was opaque. Photons bounced endlessly between charged particles, unable to travel any meaningful distance. When atoms formed, those photons were suddenly free. They streamed outward in every direction and have been traveling through the cosmos ever since, cooling as space expanded. Their wavelengths stretched from the searing glow of a 3,000-degree plasma down to the faint microwave background we detect today at a temperature of approximately 2.7 Kelvin, only slightly above absolute zero. This relic radiation fills the entire observable universe. It arrives from every direction in the sky, and its temperature is remarkably uniform. But that uniformity is not perfect. Tiny variations exist, typically only a few millionths of a degree warmer or cooler than the average. These minuscule temperature differences encode the density fluctuations that existed in the early universe, the seeds that gravity later amplified into the cosmic web of filaments and voids. Warmer spots correspond to regions that were slightly denser. Cooler spots correspond to regions that were slightly less dense. By mapping these temperature variations across the entire sky, satellites such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck spacecraft created what is essentially a baby picture of the universe. A snapshot of cosmic conditions when the universe was less than 1% of its current age. In 2004, the Wilkinson Microwave Anisotropy Probe, commonly known as WMAP, produced the most detailed full sky temperature map available at the time. When scientists examined this map, they noticed something peculiar. In the direction of the southern constellation Eridanus, there was an unusually cold patch. It spanned roughly 5 to 10 degrees across the sky and appeared about 70 millionths of a degree cooler than the surrounding cosmic microwave background. That difference may sound vanishingly small. In everyday terms, 70 millionths of a degree is so tiny that no thermometer on Earth could distinguish it from zero variation. But in the context of the cosmic microwave background, where typical temperature fluctuations measure only about 18 millionths of a degree from one region to another, this cold patch was remarkable. It was significantly colder and substantially larger than what standard statistical models of the early universe would normally predict. Scientists calculated that a region this cold and this large should appear in only about 1 to 2% of randomly generated universes based on the standard cosmological model. It was not impossible, but it was unusual enough to demand careful investigation. Something had to explain it. Several possibilities were proposed. Some researchers suggested it might simply be a statistical fluctuation, a rare but otherwise ordinary roll of the cosmic dice. Others began considering far more exotic explanations, including the theoretical imprint of a collision between our universe and another universe in a hypothetical multiverse. But the most physically grounded explanation emerged from a very different direction. What if the cold spot was not a relic of the early universe at all? What if something between us and the cosmic microwave background was causing the temperature drop? That something turned out to be an enormous cosmic void? When light from the cosmic microwave background travels across the universe on its way to our detectors, it does not arrive pristine and untouched. It must pass through 13.8 billion years of cosmic structure, moving through every filament, cluster, wall, and void that lies along the line of sight between the surface of last scattering and our instruments. Each of these structures leaves a subtle imprint on the passing photons. Dense regions exert gravitational influence, tugging on light and slightly altering its energy. Underdense regions exert far less gravitational pull, and that difference is measurable. This interaction produces an effect known as the integrated Sachs-Wolfe effect, named after the physicists Rainer Sachs and Arthur Wolfe, who predicted it in 1967. The word integrated refers to the fact that the effect accumulates along the entire path a photon travels through a given structure, adding together tiny changes in energy as it moves across cosmic distances. Here is how the process works. When a photon enters a gravitational potential well, such as the slight depression in space-time created by a concentration of matter, it gains energy. It becomes slightly blue-shifted, meaning its wavelength compresses as it falls inward. When it exits the well, it loses energy, redshifting as it climbs back out. In a static universe, these two effects would cancel perfectly. The photon would leave with exactly the same energy it had before entering. But the universe is not static. It is expanding. And that expansion is accelerating due to dark energy. During the time a photon spends crossing a gravitational region, the structure itself evolves. In a cosmic void, where dark energy dominates and gravity is weak, the void continues expanding while the photon is passing through it. The gravitational potential becomes shallower during that crossing. As a result, the photon loses slightly more energy climbing out of the potential than it gained when it fell in. It arrives at our detectors with a little less energy than it would have had if the void were not there. Less energy means a longer wavelength, and a longer wavelength corresponds to a slightly lower temperature. The photon therefore registers as slightly cooler. For small voids, this effect is negligible. The energy loss is so tiny that it disappears entirely within the background noise of other temperature variations across the cosmic microwave background. But for an exceptionally large void spanning hundreds of millions, or even billions, of light years. The cumulative effect becomes detectable. The photon spends an extraordinarily long time traversing the void, potentially millions of years. And during that entire journey, the void continues expanding. The gravitational potential becomes progressively shallower throughout the photon's passage. By the time the photon exits, it has lost measurably more energy than it gained on the way in. That energy deficit translates directly into a small temperature drop. And for the largest voids, that drop becomes visible against the otherwise uniform glow of the cosmic microwave background. Astronomers began to suspect that the WMAP cold spot might be produced by exactly such a void. In 2007, a team led by Lawrence Rudnick used radio survey data to search for an underdense region in the direction of the cold patch. They found suggestive evidence of a large void located roughly 6 to 10 billion light-years away. But the data were noisy, and the detection became the subject of intense debate. Some researchers argued that the apparent underdensity was merely an artifact caused by incomplete survey coverage. Others maintained that the signal was genuine. Only after later galaxy surveys examined that region of the sky with deeper observations and improved statistical methods did a clearer picture begin to emerge. A substantial underdensity does appear to exist in the general direction of the Eridanus Cold Spot, a supervoid roughly 1.8 billion light-years across, with a density deficit of about 20 to 30% below the cosmic average. Whether this enormous void is fully responsible for the entire temperature anomaly of the cold spot, however, remains an open question. Calculations suggest that the integrated Sachs-Wolfe effect, produced by a void of that size and depth, could account for perhaps half of the observed temperature deficit. The remainder may be a genuine primordial fluctuation originating in the early universe that happens to align with the void along the same line of sight. The most plausible explanation may therefore be a combination of both effects: a real foreground void together with a coincidental cold fluctuation imprinted in the cosmic microwave background itself. Regardless of the ongoing debate about the cold spot, the Eridanus supervoid quickly became recognized as one of the largest known structures of any kind. At roughly 1.8 billion light-years in diameter, it dwarfed every previously catalogued void. The Boötes Void, once considered extraordinary at about 330 million light-years across, would occupy only a small corner of it, a modest underdense pocket embedded within a vastly larger emptiness. The discovery demonstrated conclusively that the cosmos can produce underdense regions on scales that stretch even the most generous theoretical expectations. But the Eridanus supervoid was not the end of the story. In many ways, it was only the beginning. In 2013, 3 astronomers published a paper that would quietly introduce one of the most provocative findings in modern cosmology. Ryan Keenan, Amy Barger, and Lennox Cowie were not originally searching for a void at all. Their goal was simply to study how galaxies are distributed in the nearby universe, examining how galaxy number density changes with distance from Earth across several independent surveys. Their approach was careful, methodical, and deliberately conservative. They compiled data from multiple large galaxy catalogs covering different wavelength bands. Photometric surveys, which estimate galaxy distances based on their colors, were cross-checked with spectroscopic surveys that measure distances directly through redshift. By combining these datasets, the researchers could track how galaxy density changes as you move farther away from our location in space. This allowed them to test a fundamental assumption in cosmology: that the local universe should reflect the same average density seen on larger cosmic scales. What they discovered was a pattern so consistent and so extensive that it took time for the implications to fully sink in. In every direction they examined, out to distances of roughly 1 billion light-years from Earth, the number of galaxies fell below the expected cosmic average. Not by a trivial amount, and not by a margin that could be dismissed as incomplete survey coverage or statistical noise. The deficit was about 20%. Everywhere around us, in every direction, across a region spanning roughly 1 billion light-years. 1 out of every 5 galaxies that should exist, according to the cosmic average, was simply not there. The shortfall appeared in each survey independently. It showed up in infrared observations and in optical data. It remained present whether the team relied on photometric estimates or on spectroscopic measurements. The signal was persistent, and it appeared in every direction they examined. The pattern formed a sphere, a colossal underdense bubble centered roughly on our position in the universe, extending outward for about 1 billion light-years in radius, making the full structure close to 2 billion light-years across. The team named it the KBC Void, using the initials of their surnames, and it immediately became the largest confirmed cosmic void ever identified. The scale of the KBC Void is difficult to grasp. 2 billion light-years is not a distance the human mind easily processes. It is a number so vast that it requires comparisons just to begin approaching its meaning. Consider first that light, the fastest thing in the universe, travels at roughly 186,000 miles per second. In a single year, light covers about 6 trillion miles. Multiply that by 2 billion, and the diameter of the KBC Void reaches approximately 12 sextillion miles, a number with 22 digits. Yet even numbers that large remain abstract. They do not truly convey what it means to cross such a distance, because no human experience corresponds to scales like this. So it helps to think about it differently. Our home galaxy, the Milky Way, is about 100,000 light-years across. By any human standard, that is enormous. Light itself needs 100,000 years to travel from one side of the galaxy to the other, a time span that covers the entire arc of recorded human civilization many times over. Now imagine lining up Milky Way galaxies side by side to span the KBC Void. You would need roughly 20,000 of them placed edge to edge in a continuous row, each one a spiral galaxy containing hundreds of billions of stars, stretching across the darkness until the chain finally reached the far side of the void. 20,000 galaxies wide. That is the scale of the emptiness we appear to inhabit. Or consider it from a more familiar perspective. The nearest large galaxy to us, Andromeda, lies about 2.5 million light-years away from the Milky Way. It is the most distant object most humans can see with the naked eye, appearing as a faint smudge of light on clear autumn nights. That distance alone already feels immense. Yet you could fit roughly 800 of those Milky Way to Andromeda separations laid end to end across the diameter of the KBC Void. That is the scale of this structure. 800 Andromeda distances from one side to the other. And across most of that span, the amount of matter present falls far below what cosmology predicts should exist. The existence of the KBC Void immediately raised an uncomfortable question. If this void is so enormous, why did it take until 2013 for astronomers to recognize it? The answer lies in one of the most fundamental challenges in observational astronomy. We are inside the void. Detecting a structure that you are embedded within is extraordinarily difficult because there is no external vantage point from which to see the whole system. It is like trying to measure the size of a valley while standing at its lowest point. You can see the slopes rising around you, but without climbing far beyond them. It is extremely difficult to determine where the valley truly ends and where the surrounding landscape begins. Astronomers therefore had to infer the void's existence indirectly. They did not see it from the outside. Instead, they counted galaxies at progressively greater distances and noticed that the numbers were consistently lower than what the cosmic average predicts. The void revealed itself not as an obvious hole on a map, but as a persistent statistical shortfall appearing again and again across multiple surveys. Since that initial discovery, multiple independent analyses have confirmed the presence of the KBC Void. Different research teams using different galaxy catalogs, different survey techniques, and different portions of the sky have all arrived at essentially the same conclusion. The local universe, extending roughly 1 billion light-years in every direction, appears to be underdense by about 15 to 25% compared to the cosmic average. The exact depth and size vary slightly depending on the survey and the statistical methods used. But the central finding remains consistent. We appear to live inside a very large hole in the distribution of cosmic matter. The implications of that location are profound, reaching into some of the most precise measurements cosmologists have ever attempted. But before exploring those consequences, it is worth pausing to understand how familiar astronomical structures fit inside this enormous void. Our galaxy, the Milky Way, belongs to the local group, a collection of roughly 80 galaxies. Including our large neighbor Andromeda, the local group itself sits within a much larger structure known as the Laniakea supercluster, a vast gravitational basin containing roughly 100,000 galaxies spread across about 520 million light-years. By any normal cosmic standard, Laniakea is enormous. It is one of the largest coherent gravitational structures ever mapped in the nearby universe. Galaxies within Laniakea are not simply drifting near one another. They are moving together, flowing along vast gravitational currents toward a common center known as the Great Attractor. These coordinated motions have been measured by tracking the peculiar velocities of thousands of individual galaxies, revealing enormous streams of matter gradually converging through cosmic space. Yet, Laniakea, with all its roughly 100,000 galaxies, its thousands of galaxy groups, its many massive clusters, and its immense span of 520 million light-years, still fits comfortably inside the KBC Void. And not just barely. The void itself is roughly 4 times wider than Laniakea. Several superclusters of similar size could sit side by side within the same volume. And the region would still count as underdense by cosmological standards. This is what makes the KBC Void so conceptually unsettling. It is not empty in the everyday sense of the word. It does not resemble a room with nothing inside. Instead, it contains real structure, enormous structure, the kind of structure that, by ordinary astronomical standards, would seem remarkably rich and complex. Within this region lie superclusters, galaxy clusters, low spiral galaxies, and billions upon billions of stars steadily burning through their nuclear fuel. And yet when that same region is compared to the cosmic average, to what an equivalent volume of space elsewhere in the universe would normally contain, the numbers fall short. The matter is present, but not in sufficient quantity. The galaxies exist, but there are fewer of them than expected. The cosmic balance sheet comes up short by roughly 20%. That deficit extends in every direction for nearly 1 billion light-years. This is the key distinction between a cosmic void and the simple idea of emptiness. The Boötes Void, with fewer than 60 galaxies scattered across 330 million light-years, approaches something closer to true desolation. But the KBC Void, despite containing superclusters, galaxy clusters, and countless stars, still qualifies as underdense when measured against the overall structure of the universe. It is a region where the cosmic balance sheet fails to add up. On the larger scales, matter in the universe tends to distribute itself around a predictable average density. Yet inside this region, the numbers fall noticeably short. The deficit is significant because it is large enough to alter how the universe behaves within the void's boundaries. A 20% reduction in matter density means roughly 20% less gravitational pull shaping the region. With less gravity acting as a brake, cosmic expansion proceeds more freely. Space inside the void stretches slightly faster than space in regions where matter remains closer to the cosmic average. This difference in expansion is not theoretical speculation. it can be measured, and it carries implications that reach into some of the most precise cosmological observations ever made. Before exploring those consequences, it helps to compare the KBC Void with two other famous regions of cosmic emptiness, the Eridanus supervoid and the Boötes Void. Looking at these structures side by side reveals something important about the hierarchy of emptiness across the universe. The Boötes Void, discovered in 1981, spans roughly 330 million light-years and contains an extraordinarily deep density deficit. It is one of the most dramatically empty regions ever identified relative to its size, holding only a handful of galaxies where thousands would normally be expected. In many ways, it resembles a concentrated pocket of cosmic desolation. The Eridanus supervoid, identified partly through its imprint on the cosmic microwave background, is vastly larger. It stretches roughly 1.8 billion light-years across and exhibits a density deficit of about 20 to 30%. While far bigger than Boötes, it is not quite as empty in relative terms. And then there is the KBC Void, extending close to 2 billion light-years in diameter, with a density deficit of roughly 20%. It is the largest of the three in physical scale, though not necessarily the deepest in terms of relative underdensity. Taken together, these three structures illustrate a spectrum of cosmic emptiness. Boötes is small but extremely hollow, a region where galaxies are almost entirely absent. Eridanus is immense and moderately underdense, large enough to leave a measurable imprint on the oldest light in the universe. And the KBC Void, enormous in scale yet still populated with vast cosmic structures, sits at the boundary where emptiness begins to reshape the dynamics of the universe itself. The KBC Void stands as the most expansive of the three, a structure so immense that it envelops our entire local cosmic neighborhood and stretches far beyond the boundaries of any structure humanity has ever considered its home. Among known voids, it holds the distinction of being the largest confirmed cosmic void by sheer physical extent. That title matters not simply because of its scale, but because the physics operating inside such a vast underdensity produces measurable consequences. The larger a void becomes, the more strongly it can shape the motion of matter, the propagation of light, and even the way cosmic expansion unfolds within its domain. This is precisely why the KBC Void is no longer viewed as just an astronomical curiosity. A 20% deficit in matter spread across 2 billion light-years is not a passive irregularity in the cosmic web. It acts as a dynamic influence on the forces that structure the universe around us. Within this region, dark energy encounters less gravitational resistance. Galaxies feel a weaker collective pull from surrounding matter. Even light traveling through the void evolves slightly differently compared with photons passing through denser regions of space. In effect, many of the measurements we make about the universe, from the expansion rate of cosmic space to the estimated ages of distant objects, are subtly filtered through the environment of this enormous void. Another layer of intrigue comes from how statistically unusual the KBC Void appears to be. Cosmological simulations built on the lambda-cold dark matter model, which generally reproduce the large-scale structure of the universe with remarkable accuracy, easily generate voids on smaller and intermediate scales. But structures matching the size and depth of the KBC Void are genuinely uncommon within those simulated universes. When researchers create thousands of virtual universes and search them for voids comparable to the KBC region, only a small fraction produce anything similar. The result places the KBC Void far out on the tail of the statistical distribution of cosmic density fluctuations. Some studies estimate that a structure this extreme represents a deviation of several sigma from the expected density field. In statistical language, a 3 sigma event occurs roughly once in 700 cases. A 5 sigma event, by contrast, has odds of less than 1 in a million. The KBC Void, depending on the method of analysis, appears to fall somewhere within this statistical range, and perhaps even beyond it. The universe is capable of producing such structures through the natural amplification of primordial density fluctuations. But the likelihood is relatively small. Discovering that we may reside inside one therefore raises an uncomfortable possibility. It forces us to ask whether our location in the cosmos is unusually atypical. Whether we simply drew an improbable position in the vast cosmic lottery, or whether the theoretical models that define what counts as typical are themselves incomplete in ways we have yet to understand. This question leads directly to one of the central assumptions of modern cosmology, the cosmological principle. According to this principle, the universe should appear homogeneous and isotropic when viewed on sufficiently large scales. In other words, no region of the cosmos should be fundamentally special. The cosmological principle is far more than a technical convenience. It forms the foundation of nearly every model used to describe the universe. The equations that govern cosmic expansion, the simulations that explain how galaxies and clusters formed, and even the calculations used to estimate the age and composition of the universe all depend on the assumption that our position is not privileged or unique. Yet a void roughly 2 billion light-years across, combined with a 20% deficit in matter, represents a substantial deviation from uniformity. This is not a minor ripple in an otherwise smooth cosmic fabric. It is a major structural feature occupying a significant fraction of the nearby observable universe. And because our galaxy lies close to the center of this underdense region, our view of the universe in every direction is effectively filtered through it. If the cosmological principle holds strictly, our location should not affect the large-scale measurements we make, the expansion rate of the universe, the overall matter density, and the fundamental cosmological parameters should appear the same whether observed from inside the void or far outside it. However, the gravitational environment inside a vast underdensity is subtly different from the cosmic average. That difference introduces an unsettling possibility. Some of the measurements we interpret as universal properties might instead reflect local conditions, shaped by the particular emptiness surrounding our region of space. This tension between the assumption of large-scale cosmic uniformity and the observed reality of local underdensities has become one of the most active debates in modern cosmology. The KBC Void sits directly at the center of that discussion, a structure so enormous that it challenges the very framework scientists use to interpret the universe. The question that follows is not merely academic. It reaches deep into the very machinery of cosmic measurement. If we happen to live inside a vast void that subtly alters the local expansion rate, changes the motion of nearby galaxies, and modifies the gravitational environment through which light travels to our telescopes, then the numbers we derive from our most precise observations may contain a systematic bias that we are only beginning to recognize. The void does not simply surround us as a passive feature of the cosmic landscape. It actively influences what we observe. The universe we see through nearly 2 billion light-years of underdense space may not represent the full picture of cosmic reality. The void reshapes the gravitational conditions within it, distorts the ancient light that passes through it, subtly alters the behavior of the galaxies contained inside it, and may even lie behind one of the most persistent contradictions in modern cosmology. In that sense, the KBC Void is not just a large, empty region around us. It effectively filters the photons that reach our telescopes, slightly biases the distances we infer from astronomical observations, and can exaggerate the velocities we measure for nearby galaxies. We did not identify this void simply by observing it directly. Instead, its presence emerged gradually as scientists noticed that the numbers returned by our measurements never seemed to align perfectly with theoretical expectations. Gravity, inside a cosmic void, produces an effect that initially sounds counterintuitive. It appears to push outward. This does not mean gravity has somehow reversed direction. Gravity always pulls mass toward other mass. That fundamental rule remains unchanged. What changes inside a void is the distribution of matter, and that distribution alters the net gravitational influence experienced within the region. Once the geometry is visualized correctly, the explanation becomes surprisingly clear. Most of the matter in the universe, the dense filaments, galaxy clusters, and massive walls of the cosmic web, lies outside the void. Within the void itself, matter is relatively scarce. As a result, any galaxy located inside the void feels a stronger gravitational pull from the denser regions surrounding it than from the sparse interior. The combined effect is a subtle tug outward, drawing galaxies gradually toward the edges of the void rather than toward its center. That gravitational pull points outward toward the surrounding walls of matter, toward the filaments of the cosmic web, toward the regions where mass is actually concentrated. The consequence is a steady outward motion. Galaxies inside a void do not remain quietly suspended in place. They gradually accelerate away from the center of the void, responding to the imbalance between the thin interior and the much denser regions beyond its boundaries. This outward drift is not a subtle theoretical prediction. It is measurable, repeatable, and clearly visible in observational data. Astronomers track the motion of galaxies using a combination of redshift measurements and independent methods for estimating cosmic distances. Redshift reveals how quickly a galaxy appears to be moving away from us. But that apparent motion is actually a mixture of two different effects layered together. The first component is the expansion of space itself. The universe stretches in every direction, carrying galaxies farther apart at a rate that grows with distance. This smooth background motion is known as the Hubble flow. The second component is the peculiar velocity of the galaxy, which represents its true motion through local space as it responds to nearby gravitational structures. Every galaxy possesses both of these motions simultaneously. The redshift we observe is therefore the combined result of cosmic expansion plus the galaxy's individual movement through its local gravitational environment. Separating these two contributions from a single measurement has long been one of the central challenges in observational cosmology. Across most regions of the universe, peculiar velocities tend to be relatively small and distributed in many different directions. One galaxy may be drawn toward a nearby cluster, while another is pulled toward a different structure elsewhere. When astronomers average these motions across large volumes of space, the random directions tend to cancel out, leaving the underlying signal of cosmic expansion. Inside a void, however, that cancellation largely disappears. The peculiar velocities are no longer random. They point predominantly in the same direction, outward. Every galaxy within the void experiences the same gravitational imbalance that draws it toward the denser matter surrounding the void's edges. The result is a coherent outward flow of galaxies. This motion adds extra velocity on top of the universal expansion of space. When astronomers measure the redshift of a galaxy located inside such a region, they are observing both effects combined. The galaxy appears to be receding faster than it would from cosmic expansion alone because the outward drift from the void is layered on top of the Hubble flow. This distinction matters enormously because the number we use to describe how fast the universe expands depends on separating these two contributions with great precision. Inside a large underdense region, that separation becomes far more uncertain and difficult to untangle. The Milky Way itself participates in this outward drift. Our galaxy is moving away from the center of the nearby local void. A smaller underdense region adjacent to the much larger KBC Void, at roughly 600,000 miles per hour. This velocity is not produced by the expansion of space. It is a peculiar velocity created entirely by the gravitational imbalance of the surrounding structures. The denser regions beyond the void, including the Virgo cluster and the broader flow of galaxies within Laniakea toward the Great Attractor, pull us outward. Meanwhile, The void behind us contributes almost no gravitational pull in the opposite direction because it contains very little matter. The result is a galaxy in motion, rushing through space at a speed far greater than anything humanity has ever achieved with a spacecraft. In cosmic terms, the Milky Way is effectively sliding down a gentle gravitational slope created by the uneven distribution of matter around us. However, the local void is small when compared with the KBC void. The outflow pattern associated with the KBC region unfolds on a vastly larger scale. Galaxies located hundreds of millions of light-years from our position display the same overall behavior. They move outward from the void's interior faster than cosmic expansion alone would predict. Observations of these large-scale bulk flows, coherent motions of galaxies across enormous regions of space, repeatedly show velocities stronger than those predicted by standard cosmological models that assume a perfectly smooth universe. These flows extend outward for roughly 200 to 300 million light-years and can reach speeds of 400 kilometers per second or more. In other words, entire regions of the cosmic web appear to drift together as if carried by an invisible gravitational current. Standard lambda cold dark matter simulations have difficulty generating bulk flows of this strength across such large distances. The universe in our vicinity appears somewhat more structured, more dynamic, and more gravitationally imbalanced than the models comfortably anticipate. These motions carry a clear signature of the void itself. When researchers simulate what the velocity field should look like if a void with the size and depth of the KBC region surrounds us, the predicted motions align strikingly well with what astronomers actually observe. The magnitude of the flows, the direction they follow, and the way the velocity gradually changes with distance from the void's center all match the observational data. This consistency has become one of the clearest independent indicators that the KBC void is not merely a statistical artifact, but a real physical structure influencing galaxy motions across enormous distances. It appears to shape the dynamics of matter across billions of light-years of space. This realization leads directly into what many scientists now consider the central tension in modern cosmology. The Hubble constant is the number that describes how quickly the universe expands. It tells us that for every megaparsec of distance, roughly 26 million light-years, space itself expands at a certain velocity measured in kilometers per second. Determine the Hubble constant precisely and you effectively unlock the expansion rate of the entire universe. Once that rate is known, cosmologists can infer the age of the cosmos, estimate the density of dark energy, test the curvature of space-time, determine the ratio between matter and radiation, and predict how cosmic evolution will unfold in the distant future. Nearly every major quantity in cosmology connects back to this single parameter. It is, in many ways, the heartbeat of the universe expressed as a number. For decades, measuring it accurately has been one of the primary goals of cosmological research. The problem is that two highly precise and completely independent techniques for measuring the Hubble constant produce two different answers, and both appear internally consistent. The first method examines the ancient universe. Scientists analyze the cosmic microwave background, the faint relic radiation left over from about 380,000 years after the Big Bang. This radiation contains detailed information about the early universe, including its density, temperature distribution, and expansion conditions. By feeding these observations into the standard cosmological model, researchers can calculate what the present-day expansion rate should be. The Planck satellite performed this measurement with extraordinary accuracy. Its result indicates a Hubble constant of about 67 kilometers per second per megaparsec. The second method focuses on the nearby universe. Astronomers observe objects with well-understood intrinsic brightness, particularly type Ia supernovae and Cepheid variable stars. These objects act as reliable cosmic distance markers. Because scientists know how bright these objects truly are, They can compare that intrinsic brightness to how bright they appear from Earth. That comparison reveals the object's distance. Combine that distance with the object's redshift, and the expansion rate can be measured directly in the local universe, rather than inferred from the early cosmos. Multiple research groups using this approach, most notably the SH0ES collaboration led by Adam Rees, consistently obtain a higher value, about 73 kilometers per second per megaparsec. The gap between the two measurements is roughly 9%. In everyday terms, that might sound small, almost trivial, but both results come with extremely tight uncertainties. The outcome of decades of methodological refinement and millions of dollars invested in precision observations. The disagreement has now reached what statisticians call 5 sigma significance, meaning the probability that the difference arises from random chance alone is less than 1 in a million. In particle physics, a 5 sigma result is the threshold required to claim a discovery. In cosmology, it signals something equally serious, a genuine conflict between two ways of measuring the same universe. Both values are almost certainly correct for the phenomena they measure. The deeper issue is that the two methods may not actually be measuring the exact same cosmic quantity. This discrepancy is known as the Hubble tension, and it has dominated cosmological research for more than a decade. Numerous explanations have been proposed. Some theories introduce new physics in the early universe, suggesting a brief additional phase of expansion shortly after the Big Bang that would shift the expected expansion rate today. Others propose that dark energy might evolve over time rather than remaining constant. Still others focus on possible systematic effects in the measurements themselves. For example, dust-dimming supernovae more than expected or subtle calibration differences in Cepheid variable stars across different galaxies. Each proposal has been examined carefully, and many have failed to fully resolve the discrepancy. The tension remains. The KBC Void offers a different kind of explanation. It does not require unknown particles, altered gravity, or entirely new forces of nature. Instead, it simply suggests that our position in the universe may not be as typical as we once assumed. Here is the basic idea. The cosmic microwave background method measures the expansion of the universe averaged across its entire history. It is effectively a global measurement, sampling conditions across the whole observable cosmos. In doing so, it looks through the void and far beyond it. The value it produces, about 67 kilometers per second per megaparsec, therefore represents the average expansion rate of the universe as a whole. The local measurement using supernovae and Cepheid stars, however, probes the expansion rate only within our immediate cosmic neighborhood, and that neighborhood lies inside the KBC Void. Within the void, the outward velocity field adds extra motion to the galaxies we observe. Those galaxies are not only receding because space itself expands, they are also drifting outward due to the gravitational imbalance created by the surrounding underdensity. When we measure their redshifts, we detect both effects combined. The result is a local expansion rate that appears faster than the true cosmic average. When astronomers analyze nearby supernovae, they are not measuring the pure expansion of the universe. They are measuring cosmic expansion, combined with the outward drift produced by the void, and interpreting that combined motion as if it were expansion alone. The strength of this effect has been studied in detail. Models show that a void roughly 2 billion light-years across, with about a 20% deficit in matter density, can generate an outward flow large enough to increase the apparent local Hubble constant by roughly the amount required to bridge the gap between 67 and 73. The agreement is not perfect, and different studies produce slightly different numbers depending on the assumed structure of the void. But the scale of the effect and its direction are both consistent with what observations require. The presence of the void naturally makes the local universe appear to expand faster, which is precisely what astronomers measure. If the void explanation is correct, The Hubble tension would not signal new physics. Instead, it would reveal that some of our assumptions were flawed. For decades, cosmology assumed that our position in the universe was typical and that local measurements could be safely treated as global ones. The KBC Void suggests that those assumptions may not hold in our particular region of space. In that case, the theoretical framework of cosmology may remain mathematically sound. But its interpretation could be distorted by the unusual emptiness surrounding our galaxy. The implications extend far beyond the Hubble constant itself. If the local expansion rate is artificially inflated by the void, then any calculation using that larger value to estimate the age of the universe will produce an age that is too young. Measurements derived from the cosmic microwave background suggest the universe is about 13.8 billion years old. However, if the higher local value of the Hubble constant were interpreted as a universal number, the age of the universe would shrink to roughly 12.7 billion years. That younger estimate immediately creates a problem. The oldest known stars in the halo of the Milky Way, particularly those in ancient globular clusters, have ages estimated at around 13 billion years. Based on well-established models of stellar evolution, a universe only 12.7 billion years old cannot logically contain stars that are 13 billion years old. The numbers simply collide. But if the void hypothesis resolves the Hubble tension by explaining the higher local value as a consequence of void-driven outflow rather than true cosmic expansion, the paradox disappears. The universe returns to an age of 13.8 billion years. The ancient stars fit comfortably within that timeline. And the apparent contradiction turns out to be an observational illusion created by our position inside a vast cosmic void. But the void does more than bias expansion measurements. It fundamentally alters the environment in which galaxies form and evolve, creating conditions that differ sharply from those in the dense filaments and clusters of the cosmic web. Galaxies inside cosmic voids grow up in isolation. In dense regions, galaxies lead crowded and turbulent lives. They pass close to neighboring systems again and again. Gravitational encounters strip gas from their outer layers. Collisions and mergers ignite powerful bursts of star formation that rapidly consume their available fuel. Close interactions with massive companions can distort galactic shapes, twist spiral arms, and funnel streams of matter toward their central supermassive black holes. Over billions of years, these repeated encounters reshape galaxies. Spiral galaxies gradually merge into ellipticals. Star-forming systems burn through their gas reserves and fade into red. Quiet galaxies with little new stellar activity. The dense environment speeds up this transformation, pushing galaxies through their evolutionary stages far more quickly. Void galaxies experience almost none of this chaos. The distances separating them from their nearest neighbors are so enormous that gravitational encounters become extremely rare. Mergers occur only occasionally, and sometimes not at all, across billions of years. Without the constant disturbances found in crowded regions, galaxies inside voids evolve slowly and steadily, guided mostly by their own internal processes rather than by environmental pressure. The result is a population of galaxies that looks strikingly different from those found in filaments or galaxy clusters. Void galaxies are typically smaller and less massive than galaxies in dense environments. Most belong to late-type systems, meaning spirals and irregular galaxies, rather than the giant ellipticals that dominate the centers of galaxy clusters. Their shapes are often remarkably undisturbed. Many show smooth, rotating disks and clean rotation curves, with little evidence of the gravitational harassment common in crowded cosmic neighborhoods. In many ways, they resemble galactic fossils, preserved in conditions that have remained relatively calm for billions of years. One of the most distinctive properties of void galaxies is their unusually high gas content. In dense environments, several physical processes gradually remove gas from galaxies over time. Ram pressure stripping occurs when a galaxy moves rapidly through the hot gas that fills galaxy clusters. The pressure of this medium pushes cold hydrogen gas out of the galaxy. Much like a strong wind tearing leaves from a tree, tidal interactions during close gravitational encounters can also pull gas outward into long streams stretching between neighboring galaxies. Over time, these streams disperse into intergalactic space. Another process, known as starvation, is more subtle. It happens when the extended halo of hot gas surrounding a galaxy is stripped away by the cluster environment. Without that halo, the galaxy loses its supply of fresh gas that would normally cool and fall back onto the disk, fueling future generations of star formation. Even the intense radiation and energetic jets produced by nearby active galactic nuclei can heat surrounding gas and prevent it from cooling enough to collapse into new stars. A process astronomers call feedback inside cosmic voids. However, these mechanisms are largely ineffective. Void galaxies tend to retain their gas for extremely long periods of time. Vast reservoirs of neutral hydrogen remain in place, never compressed into stars, never stripped away by gravitational encounters, and never heated beyond the point where collapse becomes possible. Many of these galaxies rank among the most gas-rich systems known, containing proportionally far more raw material for star formation than galaxies of similar size in crowded cosmic environments. This abundance of gas creates an interesting paradox. Void galaxies often possess more fuel for star formation, yet their actual star formation rates are typically lower than those seen in dense regions of the universe. The explanation lies in the conditions required to trigger the birth of stars. Gas does not simply collapse into stars on its own. It usually needs an external disturbance, some form of compression that raises the local density high enough for gravity to take over. In crowded environments, these triggers occur frequently. Galaxy collisions and mergers compress gas clouds. Shock waves from nearby supernova explosions ripple through intergalactic space. Passing galaxies create tidal forces that squeeze gas within their neighbors. Inside voids, most of these triggers are absent. The gas often sits quietly in extended reservoirs, stable and largely undisturbed, waiting for a compression event that may never occur. Star formation still takes place, but it tends to proceed slowly, driven by internal processes such as spiral density waves rather than by dramatic external disturbances. Yet when star formation does ignite in a void galaxy, it can become surprisingly powerful. Because these galaxies hold such enormous stores of gas, any event capable of compressing a substantial fraction of that material can produce a starburst, a brief but intense episode of rapid star formation. In some cases, void galaxies display bursts of stellar creation that rival those seen in the most active regions of galaxy clusters, powered by the vast reserves of gas that have remained untouched for billions of years. These bursts are usually triggered by internal instabilities within the galaxy itself, rather than by external encounters. That makes them fundamentally different from the merger-driven starbursts commonly observed in crowded galaxy clusters. The chemical composition of void galaxies offers another important clue about their slow and isolated evolution. Stars manufacture heavy elements through nuclear fusion and release them into surrounding gas when they die. With each new generation of stars, the gas inside a galaxy becomes richer in heavier elements. Astronomers refer to this gradual enrichment as chemical evolution. Because void galaxies form stars more slowly, they have produced fewer generations of stars over cosmic time. As a result, they tend to show lower metallicities, meaning their gas contains fewer elements heavier than helium compared with galaxies living in dense regions of the cosmic web. This lower metal content confirms that void galaxies have been evolving at a slower pace, converting their primordial gas into stars and heavy elements far more gradually than galaxies in the busy filaments and clusters of the universe. The dark matter halos surrounding void galaxies also show important differences. Every galaxy sits within a much larger halo of dark matter, an invisible gravitational structure that extends far beyond the visible stars and gas. In dense regions, these halos constantly interact with nearby halos. Gravitational tides stretch them, distort them, and sometimes strip away their outer layers. Inside voids, those disturbances are rare. Dark matter halos remain more symmetrical and largely undisturbed, maintaining their shape over billions of years without the tidal stresses that reshape halos in crowded clusters. Because of this stability, void galaxy halos become exceptionally clean laboratories for studying dark matter itself. Since their structure is influenced mainly by the intrinsic properties of dark matter rather than by complex environmental effects, the study of void galaxies has therefore transformed these seemingly empty regions from astronomical backwaters into powerful scientific laboratories. By comparing galaxies in voids with galaxies in dense clusters, astronomers can separate the influence of internal physics from the influence of environmental forces in galaxy evolution. Some properties arise from the galaxy's own mass, rotation, and gas supply. Others are shaped by its surroundings, the frequency of interactions, the density of nearby matter, and the gravitational pull of neighboring structures. Void galaxies serve as a kind of control group, representing what galaxy evolution looks like in near isolation. Any systematic differences between void galaxies and cluster galaxies reveal how strongly the surrounding cosmos can shape the galaxies within it. This laboratory role extends beyond galaxy evolution to the fundamental physics of the universe itself. Cosmic voids are among the only places where dark energy dominates the dynamics almost completely. In galaxy clusters, gravity is strong enough to bind matter together and resist cosmic expansion. In filaments of the cosmic web, gravity still provides significant resistance. But inside voids, where matter is sparse and gravitational forces are weak, dark energy drives the expansion of space with very little opposition. Voids expand faster than the cosmic average precisely because dark energy encounters so little gravitational resistance within them. This makes cosmic voids natural environments for testing the properties of dark energy with greater clarity. Dark energy remains one of the deepest mysteries in modern physics. It was first identified in 1998 through observations of distant Type Ia supernovae. And today it appears to make up about 68% of the total energy content of the universe. Unlike matter and gravity, dark energy behaves in the opposite way. Instead of pulling structures together, it pushes space apart. Rather than slowing cosmic expansion, it accelerates the growth of the universe itself. Yet its fundamental nature is still unknown. One possibility is that dark energy is a cosmological constant, an unchanging energy density embedded in the fabric of spacetime itself. Another possibility is that it represents a dynamic field whose strength varies across time or space. Distinguishing between these scenarios requires extremely precise measurements of how the universe expands under different conditions and at different stages of cosmic history. Cosmic voids offer some of the cleanest environments for making these measurements. In dense regions such as galaxy clusters, the strong gravitational pull of nearby matter complicates the expansion signal. The motions of galaxies there are influenced by many overlapping gravitational forces, making it difficult to isolate the effect of dark energy alone. Inside voids, those complications are greatly reduced. Galaxies move primarily under the combined influence of cosmic expansion and dark energy, with very little gravitational interference from surrounding matter. By measuring how galaxies move relative to the edges of voids, how rapidly voids grow over cosmic time, and how the shapes of voids evolve as the universe ages, astronomers can probe the properties of dark energy with fewer systematic distortions. The shape of voids provides especially powerful clues. If dark energy truly behaves as a cosmological constant that is uniform everywhere in space and constant over time, then voids should expand evenly in every direction. As they grow, they should remain roughly spherical. But if dark energy varies across space or changes over time, voids might expand unevenly. They could become stretched, elongated, or distorted in ways that reveal the underlying physics. Observing the shapes of voids at different cosmic epochs therefore allows scientists to test whether dark energy is truly constant or whether it hides a more complex and evolving nature. So far, measurements suggest that dark energy has remained approximately constant over the past several billion years, consistent with the simplest cosmological models. However, the uncertainties are still large enough that more exotic possibilities cannot yet be ruled out. Future astronomical surveys will dramatically improve these measurements. Missions such as the Euclid Space Telescope and the Vera C. Rubin Observatory will map thousands of cosmic voids across a wide range of distances. Each of those voids will act as an independent probe of how dark energy influences the expansion of the universe. Among them, the KBC Void, because it is both enormous and relatively close to our cosmic neighborhood, offers one of the most detailed natural laboratories currently available for studying these fundamental questions. Its proximity allows measurements with a level of precision that would be impossible for more distant voids, making it a crucial target for future dark energy research. Because the KBC Void lies relatively close to our cosmic neighborhood, astronomers can study its structure and dynamics in far greater detail than the enormous voids detected at extreme distances. The physics operating inside the void also influences observations of objects located far beyond its boundaries. Light from distant galaxies, supernovae, and quasars must pass through the KBC Void before reaching our telescopes. As this light crosses the underdense region, it interacts with the void's gravitational environment and its slightly faster expansion rate. Over vast distances, these subtle effects accumulate. The wavelength and energy of the traveling photons are altered just enough to influence how astronomers interpret the sources that emitted them. Another clue appears in measurements of baryon acoustic oscillations, the faint imprint of sound waves that traveled through the early universe. These oscillations act as standard cosmic rulers, allowing scientists to measure distances across enormous scales of space. However, when these measurements are made within the region influenced by the void, small discrepancies appear compared with observations taken far outside the void's boundaries. Those differences match the prediction that the void slightly inflates our local measurement of cosmic expansion. Each line of evidence strengthens the case. Bulk flow measurements match the velocity patterns predicted by a large surrounding void. The Hubble tension aligns with the expected expansion bias produced by void-driven outflow. Baryon acoustic oscillations reveal the subtle local distortions predicted by void models. And the populations of galaxies inside the void display the evolutionary differences expected for galaxies growing in such an environment. Taken together, these observations suggest that the KBC Void is not a single isolated anomaly. It forms part of a broader framework that explains several otherwise puzzling features of the nearby universe. Whether this framework ultimately proves sufficient, or whether additional physics will be required to fully resolve the tensions within cosmology, remains an open question. But the existence of the void itself is no longer seriously in doubt. The deeper question now is what such an enormous, underdense region, combined with the fact that voids dominate the cosmic web, reveals about the fundamental nature of the universe. If voids occupy roughly 80 to 90% of the total cosmic volume, if the largest among them stretch for billions of light years and include our own position, and if these regions continue expanding with each passing epoch, then the universe we inhabit is not primarily defined by the galaxies and stars we celebrate. It is defined by the vast spaces between them. Those immense empty regions may hold critical clues about where the universe came from and how its future will unfold. The void surrounding us has influenced the galaxies that formed within it, altered the light that travels through it, and subtly shifted the expansion rate we measure from our position inside it. Every observation we make carries some imprint of that environment. The question is no longer whether the void matters. The real question is whether the universe can be fully understood without accounting for the immense regions where almost nothing exists. When confronting the enormous scale of cosmic voids, there is a natural tendency to treat them simply as features within the universe. There is a tendency, when we think about cosmic voids, to treat them as secondary features of the universe, as if the universe itself is the primary structure, and voids are merely the gaps left behind, holes punched into an otherwise complete cosmic fabric. It is natural to imagine the cosmos as a place defined by matter, energy, and structure, with empty regions appearing only where those ingredients happen to run out. But that perspective may actually be reversed. Consider the arithmetic of the observable universe, the observable cosmos, the region from which light has had enough time to reach Earth since the Big Bang. Extends roughly 40.6 billion light-years in every direction. Within that immense sphere lies the entire stage on which cosmic history unfolds. Every galaxy ever observed, every star whose light has reached our instruments, and every atom of hydrogen, helium, carbon, and iron that has participated in the long story of cosmic evolution exists somewhere within this enormous volume. Now divide that volume according to how matter is actually distributed. The filaments, walls, clusters, and superclusters that make up the cosmic web. The structures that contain nearly all visible matter in the universe occupy only about 10 to 20% of that total space. Everything else, the remaining 80 to 90%, belongs to the voids. This number is often quoted, but its meaning is rarely fully absorbed. Numbers can be repeated without their implications truly being understood. And the implications of this particular number are profound. If you could drop a pin at a completely random location anywhere within the observable universe, with perfect mathematical randomness and no bias toward galaxies or clusters, the overwhelming probability is that the pin would land inside a void. Not near a galaxy, not along a filament, not anywhere close to a major gravitational structure. It would fall into a region of space so sparsely populated that the nearest significant galaxy might lie hundreds of millions of light-years away in every direction. From that vantage point, the universe would appear almost entirely empty. The darkness would stretch so far and contain so little that, for all practical purposes, the cosmos would look like a vast and nearly featureless expanse. And that outcome would not be unusual. It would be the typical one. Voids are not the exception in the universe. They are the dominant environment. Galaxies are the rare structures embedded within that much larger emptiness. This reversal of perspective can be difficult to grasp because nearly every image we have ever produced of the universe emphasizes the opposite view. Telescopes are designed to collect light. Cameras are aimed at objects that shine. Astronomical surveys map the positions of galaxies because galaxies are what our instruments detect. For centuries, the progress of astronomy has largely meant improving our ability to find luminous objects within the darkness. From Galileo's first telescope to the James Webb Space Telescope, every technological leap has increased our ability to gather faint light and detect distant cosmic sources. The images produced by these instruments create a powerful impression of abundance. One of the most famous examples is the Hubble Deep Field, an image that revealed roughly 10,000 galaxies within a patch of sky, no larger than a grain of sand held at arm's length. The photograph gives the impression of a universe overflowing with structure, packed with galaxies in every direction. But that image reflects a profound selection effect. It shows only the locations where light originates. What it cannot reveal are the vastly larger regions between those points of light. The immense volumes of space where almost nothing exists and almost nothing shines. If you could somehow create an image that gave equal visual weight to every cubic megaparsec of space in the observable universe, including the voids, the galaxies would not dominate the frame. They would appear only as faint specks scattered across an immense field of darkness, stretching to every edge of the image without interruption. The origins of this cosmic architecture reach back to the earliest moment the universe allows us to examine, within the first fraction of a second after the Big Bang. The cosmos underwent a brief but extraordinary phase of expansion known as inflation. During this epoch, which may have lasted only about 10 to the minus 36 seconds, the observable universe expanded by an almost unimaginable factor of 10 to the 26th power. Space expanded so rapidly that regions which had once been close enough to exchange energy and information were hurled apart to distances that light would need billions of years to cross. Inflation helps resolve several deep puzzles in cosmology. It explains why the universe appears geometrically flat, why the cosmic microwave background is nearly uniform in temperature across the sky, and why certain exotic particles predicted by early particle physics, such as magnetic monopoles, have never been observed. But inflation also produced another consequence, one that shaped the entire future structure of the universe. It stretched microscopic quantum fluctuations to cosmic scales. Quantum mechanics tells us that the vacuum of space is never perfectly empty. Even in a region containing no particles or radiation, energy fluctuates at extremely small scales. Virtual particles briefly appear and disappear, borrowing energy from the vacuum for such short intervals that the uncertainty principle prevents them from being directly observed. Fields throughout the universe jitter and oscillate around their lowest energy states. The electromagnetic field, the Higgs field, and every other quantum field permeating reality vibrate continuously with tiny fluctuations. These disturbances occur at scales trillions of times smaller than an atomic nucleus. Under ordinary conditions, they average out and have no noticeable consequences for larger structures such as atoms, planets, or stars. They are simply the faint background noise of physical reality. Inflation changed that situation dramatically. During the first instance of cosmic expansion, space expanded so quickly that these microscopic fluctuations were stretched across enormous distances. Tiny variations in energy density were amplified to scales that would later span millions or even billions of light years. A fluctuation that began smaller than a proton could be stretched to a size larger than a future galaxy cluster. A minute excess of energy in a region smaller than an electron became the seed that would slowly grow, over billions of years, into a filament of the cosmic web containing countless galaxies. A fluctuation that represented a tiny deficit of energy became the seed of something very different. Over immense stretches of time, that deficit would grow into a cosmic void spanning hundreds of millions of light years. Inflation stretched these fluctuations so quickly and so completely that, by the time the process ended, they were effectively frozen into the structure of space itself, imprinted as permanent variations in energy density. Some regions ended up with infinitesimally more energy than the cosmic average, while others contained infinitesimally less. The differences were astonishingly small, roughly 1 part in 100,000. At first, such variations were so slight that they would have been impossible to detect and would remain nearly invisible for hundreds of millions of years. But they were real. They were permanent. And gravity, the most patient force in the universe, would spend the next 14 billion years slowly amplifying them into the vast structures we observe today. In the regions that began slightly denser than average, gravity gained an early advantage. A little extra matter produced a slightly stronger gravitational pull. That pull attracted more matter from the surrounding space. which increased the gravitational attraction even further. This feedback loop unfolded gradually but relentlessly. Over the first few 100 million years, the overdense regions grew stronger. Their density contrasts rose from 1 part in 100,000 to 1 part in 1,000, and eventually to 1 part in 100. Eventually, the densest regions crossed a critical threshold and began collapsing inward under their own gravity. The first structures to form were dark matter halos, vast invisible concentrations of mass that served as the gravitational framework for everything that followed. Within these halos, ordinary matter began to fall inward. Gas was compressed and heated, then cooled by radiating energy away into space. Over time, it fragmented into dense clouds capable of igniting nuclear fusion. The first stars were born. Across billions of years, stars formed, lived, and died. Each generation enriched the surrounding gas with heavier elements. Galaxies gradually assembled as smaller protogalactic fragments merged together. Galaxy groups formed along the growing filaments of the cosmic web, flowing toward the dense nodes where clusters would eventually emerge. Over cosmic time, these structures grew in mass and complexity, building the luminous architecture of galaxies, clusters, and filaments that fill the universe today. In the regions that began slightly less dense than average, the opposite process unfolded with the same quiet inevitability. A small deficit of matter meant slightly weaker gravitational pull. Nearby, overdense regions gradually drew matter away from these areas, pulling it outward along gravitational gradients much like water flowing downhill. These underdense regions slowly expanded as their surroundings grew denser. As matter drained away, they became wider and more shallow over hundreds of millions and eventually billions of years. They became the first cosmic voids. At first, they were small, but they steadily expanded as matter continued flowing outward. Over the last several billion years, as dark energy began to dominate the dynamics of the universe, the expansion of these voids accelerated even further, pushing them to grow larger and emptier with each passing epoch. The emptiest regions of the universe became emptier still, inflating outward against the thinning walls of the cosmic web with a momentum that will never be reversed. The entire architecture of the observable universe, every filament, every cluster, every supervoid stretching billions of light years across, traces its origin to quantum noise, randomness at a scale smaller than an atom, operating during an interval shorter than any clock could measure, propagated upward through billions of years of gravitational evolution to produce structures so vast that light itself requires billions of years to cross them. The seeds of the KBC Void were planted before matter existed, before atoms formed, before the four fundamental forces had fully separated from the unified state of the earliest cosmos. The largest void ever found began as a whisper of quantum probability in the first trillionth of a trillionth of a trillionth of a second. This connection between the infinitely small and the unimaginably large is one of the most remarkable facts in all of science. The cosmic web is not the product of some grand structural principle or organizing intelligence. It is the amplified residue of quantum randomness, a monument to chance built by gravity over cosmic time. The voids exist because certain patches of quantum foam happen to fluctuate downward rather than upward during an epoch so brief that no physical process could have controlled or directed the outcome. Had those fluctuations unfolded differently, the voids would lie elsewhere. The filaments would trace entirely different paths, and the galaxies we know might never have formed at all. Every star in the night sky, every planet orbiting those stars, every atom in every living thing that has ever existed on any world owes its place in the cosmos to a random event that occurred before the universe was old enough to possess the physical structures we recognize today. But the story of cosmic voids does not end with their origins. It continues into a future that stretches far beyond the present cosmic epoch. And that future belongs, increasingly, to the voids themselves. Dark energy is accelerating the expansion of the universe. This acceleration has been measured through multiple independent methods, including observations of distant type Ia supernovae, the geometry of the cosmic microwave background, and the clustering patterns of galaxies across cosmic time. It is one of the most firmly established and yet most mysterious discoveries in modern cosmology. No one truly knows what dark energy is. No one understands why it possesses the value it does, or why it exists at all. But its effects are undeniable, and they are steadily reshaping the cosmos on the largest scales. The acceleration is gentle at present, almost imperceptible across the span of a human lifetime, or even the lifetime of entire civilizations. Space itself is expanding faster with each passing second, yet the rate of increase remains slow enough that gravitationally bound systems, galaxies, galaxy groups, and some tightly bound clusters can still hold themselves together against the outward push. The gravitational attraction between the Milky Way and Andromeda is strong enough to overcome the expansion of the intervening space. In roughly 4 to 5 billion years, the two galaxies will merge. Regardless of what dark energy does in the meantime, the local group, our modest family of roughly 80 galaxies, will likely remain gravitationally bound as a single coherent structure far into the cosmic future. Some of the most massive galaxy clusters, held together by deep gravitational wells filled with hot gas and dark matter, will persist as well. But beyond these gravitational islands, beyond the boundaries where gravity yields to cosmic expansion, dark energy is winning. And it is winning fastest inside the voids, where gravity is weakest, where matter is scarcest. Dark energy encounters almost no resistance. The voids are not merely expanding, they are accelerating their expansion, growing faster with every passing cosmic epoch. Their boundaries push outward into the surrounding filaments, compressing them, thinning them, slowly eroding the structures that define the cosmic web, over time scales of tens of billions of years. This process will dismantle the web itself. The filaments will thin until they can no longer sustain the flow of matter between clusters. Galaxy groups that are not gravitationally bound will drift apart, their connections to the cosmic web severed by the expanding voids between them. Walls of galaxies will stretch and dissipate as the voids on either side grow larger and push them apart. Individual galaxies on the outskirts of groups will find themselves abandoned, their neighbors receding at ever-increasing velocities until they slip beyond the gravitational reach that once held the group together. The cosmic web, which today is the largest coherent structure in nature, a network of gravitational connections spanning the entire observable universe, will gradually unravel. Its threads will snap one by one. Its nodes will become isolated. The connective tissue that links distant parts of the cosmos into a single gravitational system will dissolve, replaced by ever-widening expanses of void that no signal, no particle, no force can bridge. The timescale for this dissolution is long but finite. Within roughly 100 billion years, an interval approximately 7 times the current age of the universe, the cosmic web will have largely disappeared. What remains will be a scattering of isolated galaxy clusters, each one a gravitationally bound island surrounded by an effectively infinite expanse of expanding void. These clusters will still contain galaxies. Stars will still burn within them, though the stellar populations will by then be dominated by dim, long-lived red dwarfs burning through their hydrogen fuel with agonizing slowness, each one capable of shining for trillions of years, yet producing only a faint fraction of the light our sun generates today. New star formation will have largely ceased as the available gas is consumed or expelled beyond recovery. The raw material for building new stars will simply run out. The clusters themselves will slowly evolve over trillions of years. Their remaining galaxies merging one by one through gravitational friction until each cluster is reduced to a single enormous galaxy. A bloated elliptical containing the combined remnant mass of everything that once orbited within its gravitational reach. Beyond the edges of these island galaxies, the voids will stretch without interruption in every direction. The space between isolated clusters will expand so rapidly that light emitted from one cluster will never reach another. Photons that set out on the journey will find themselves running against an expansion that outpaces them. The distance growing faster than light can cross it. Each island galaxy will occupy its own observable universe. A shrinking bubble of visibility within an endlessly expanding void. Over trillions of years, the cosmic microwave background will redshift beyond detection. Its photons stretch to wavelengths longer than the observable universe itself. The evidence that a Big Bang ever occurred will slowly fade from view. The other galaxy clusters, the ones that once shared the cosmic web and helped shape the grand architecture of the observable universe, will vanish beyond the horizon one by one. Their light redshifted into silence. From the perspective of any astronomer living on a planet orbiting a dim red dwarf within one of these island galaxies, the universe will appear to contain only their own galaxy. Every other structure will have receded beyond the cosmic horizon, carried away by the relentless expansion of the void into a darkness that is both total and permanent. Such an Astronomer, examining the sky with whatever instruments their civilization has built, would find no evidence that the cosmic web ever existed. No filaments, no superclusters, no background radiation hinting at a hot and dense beginning. They would observe a single aging galaxy floating in an apparently infinite, static, and utterly empty void. And they would have no reason to suspect that the universe had ever been otherwise. This is the final state toward which the cosmos is evolving. Not a dramatic collapse into a singularity. Not a violent tearing apart of atoms and particles in some catastrophic rupture. Not a cyclical rebirth offering the hope of renewal. Instead, it is a slow, silent, inexorable expansion of emptiness. The voids will not merely persist as features of the cosmic landscape. They will eventually dominate everything they do not already contain. Given enough time, stretching into the trillions and quadrillions of years, voids will occupy not 80 or 90% of cosmic volume, but effectively all of it. The matter that once formed galaxies and stars and planets will still exist, locked inside cooling stellar remnants and slowly evaporating black holes within isolated clusters. But it will constitute an infinitesimally thin fraction of a cosmos that has become, for all practical purposes, entirely void. The universe will not end with a bang. It will end with a silence so complete that nothing will remain capable of noticing that it has fallen silent. There is a particular kind of discomfort that accompanies this picture. It is not fear exactly. Fear requires an immediate threat. And the expansion of cosmic voids threatens nothing on any human timescale. The sun will exhaust its hydrogen fuel and swell into a red giant billions of years before the cosmic web finally unravels. Humanity, in whatever form it takes by then, will face countless challenges far more immediate and personal than the dissolution of galactic filaments 100 billion years in the future. The unease comes from something else entirely. It comes from a quiet realization. The universe we see around us tonight, the one filled with galaxies, glowing nebulae, and the steady light of hundreds of billions of stars, is not what the universe fundamentally is. It is only a temporary arrangement, a brief configuration of matter that happens to exist during this narrow window of cosmic history. When the cosmic web is still intact and the voids have not yet completed their slow and patient work, we happen to live during the universe's most structured era, Right now, the cosmic web is near the peak of its complexity. In this moment of cosmic time, the filaments are as dense as they will ever be. The clusters are as rich as they will ever become. The great walls of galaxies still hold their shape, and the voids between them are still contained. The contrast between emptiness and structure is as sharp as it will ever appear in the history of the universe. But this moment is temporary. From here, across the immense span of billions and trillions of years, the direction begins to change. The voids slowly grow larger. The filaments slowly thin. The sharp contrast between structure and emptiness begins to soften. Matter spreads outward across ever larger volumes of expanding space. Structures that required billions of years to assemble will slowly fade, diluted by an expansion that never stops and never grows tired. When we point our telescopes toward the night sky and capture images of galaxy clusters, luminous nebulae, and the delicate lacework of the cosmic web, we are witnessing the universe at its architectural peak. This is the moment when the cosmos is most intricate, most luminous, most richly connected, and it will never look quite like this again. Across the long future of cosmic time, the pattern will slowly simplify. Structure will fade. Light will grow rarer. The universe will become quieter, darker, and more spacious with each passing epoch. Not through violence or catastrophe, but through a slow and patient unfolding of expansion. The great KBC Void, the enormous region of underdensity that contains our galaxy and our entire local supercluster, is not an anomaly, it is a preview. It shows us what much of the universe already looks like, and what the entire universe will eventually become. 2 billion light-years of sparse matter surrounding us in every direction. Galaxies exist within it, but not enough to fill the darkness. Structures are present, but thin and widely scattered. And from within this immense region, we cannot see its edges. This is not a strange corner of the cosmos. In many ways, this is the cosmos. Most of the universe already looks like this. The bright filaments and crowded clusters that fill astronomical images are the exception, not the rule. And with time, even those islands of structure will slowly diminish. What makes this realization unsettling is not danger. Nothing about this future threatens us tonight. The stars above us will continue to shine for billions of years. The galaxies will continue their slow gravitational dance. Life, on whatever worlds it may arise, will still experience warmth, light, and wonder. The unease comes from something quieter. It comes from understanding that we are living in the brief moment when the universe is most alive with structure. A fleeting chapter in an unimaginably long cosmic story. A moment when the lights are still on across the great halls of the cosmos, before the rooms slowly empty and the silence gradually returns. And perhaps that realization is not meant to frighten us. Perhaps it is simply meant to remind us how extraordinary this moment truly is. Tonight, when you look up at the stars, you are not just seeing distant suns scattered across space. You are witnessing the universe during the rarest phase of its entire history. A time when galaxies still gather into filaments, when clusters still glow with billions of stars, and when the vast emptiness between them has not yet taken over everything. This is the cosmos at its brightest chapter. And for now, at least, we are here to see it. So let the universe continue its slow unfolding. Let the voids expand in their patient way. None of it will change the quiet beauty of the sky above us tonight. Rest beneath those distant stars. Let the vastness of the cosmos carry your thoughts gently outward. And if the universe truly is moving towards silence, then for now, we are living in the moment when the music is still playing. Good night. Sleep well under the stars.